Let's move on to part C, where we manipulate a known. In number 1, I want to come up with a power series for the cosine of x. I certainly can raw construct it, but for the purpose of this lesson, I want to show you how you change or manipulate known series. So what do we know? So first, I want to write what I know. I know that the sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus plus negative 1 to the n x to the 2n plus 1 all over 2n plus 1 factorial plus I know that that is true. I also know that that has an interval of convergence of all real numbers. Next, I want to note that the cosine of x is equal to the derivative with respect to x of the sine of x. So now I'm going to do that. So the cosine of x equals the derivative with respect to x of the power series that I know for sine of x, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus let's write the next one, x to the 7th over 7 factorial plus plus negative 1 to the n x to the 2n plus 1 over 2n plus 1 factorial plus And then I'm actually going to do this. I'm going to take the derivative term by term by term. So the derivative of x is 1. And then it's going to be minus, I bring down the 3 and it cancels out with 3 factorial, but not completely. So it's going to be x squared over 2 factorial plus, can you say what the next one is? 5's cancel out, x to the 4th over 4 factorial. I'm just taking the derivative term by term by term. X to the 6 over 6 factorial plus And we could actually take the derivative of the nth term or just determine the new pattern with the values that we have. So this is negative 1 to the n. That's a constant when we're doing derivative in terms of x. So the 2n plus 1 cancels out with the 2n plus 1, and we have x to the 2n power over 2n quantity factorial plus Awesome. We have a new power series, and that is the one for the cosine of x, 0 to infinity, negative 1 to the n, strictly alternates, x to the 2n over quantity 2n factorial. And awesomely enough, that is going to converge for all real numbers. How do I know that? Because I've done it 1,000 times, and also the ratio test would tell us that it converges for all real numbers. Second one, f of x is given. What do we know? We have to pick something we know that sort of looks like this. We know that 1 over 1 minus x, we've done this twice as a geometric, and then raw construction is 1 plus x squared plus plus x to the power of n plus So that's something we know. And how do these two relate? The key to this manipulated known is what is the known and how do I manipulate it to look like f? So do you see it? Do you see that the derivative with respect to x of 1 over 1 minus x actually equals 1 over 1 minus x quantity squared? Hopefully you do. So now we're going to do this. We're going to say 1 over 1 minus x quantity squared is equal to the derivative with respect to x of this, and we're going to do it now. We're going to do term by term. Let's write out these terms. 1 plus x squared plus plus x to the n plus and do the derivative term by term by term. So the derivative of 1 is 0, then the derivative of x is 1, then we have plus 2x plus Now had the other one in there, x cubed, it would be 3x squared plus dot 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 plus n times x to the n minus 1 plus dot dot dot. And now for this known one, the interval of convergence was between -1 and 1. When you find the derivative, you cannot gain any points of interval. Let me say that again. This is my interval of convergence for my known. If I'm taking the derivative of a power series, I'm not going to suddenly have 1 become a part of the interval. So it would never turn out that my manipulated one would look like this, because I can't gain the point of 1 by taking the derivative. I can only perhaps lose points. So it will turn out that the interval of convergence is the same as it was for the known. And that does happen frequently, but not all the time. Number 3, f of x is the natural log of 1 plus x. Ooh, this one is so fun. Known. Oh geez, I know a series for 1 over 1 plus x. That's not as terribly obvious as some of the others, but a series for this, if you remember, common ratio negative x, so we have 1 minus x plus x squared minus x cubed plus x to the 4th minus dot 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 plus x to the power of n. Oops. -1 to the n, x to the power of n, plus dot dot dot. So that's what we know. And now, ooh, fun now here. How does the natural log of 1 plus x relate to 1 over 1 plus x? The natural log of 1 plus x equals the integral, now this is where it gets fun, from 0 to x 1 over 1 plus, using the dummy variable t dt. So in other words, the natural log of 1 plus x is the integral of 1 over 1 plus x. But I wrote it in this really fun form. So let's do this. Now I'm going to find the integral from 0 to x of the power series that we know for 1 over 1 plus x, written in a dummy variable. So it's 1 minus t plus t squared minus t to the 3rd plus dot 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 plus -1 to the n t to the n plus dot 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 dt. And that's okay. Now to note that the interval of convergence for the known was x is between -1 and 1. So we're integrating now term by term by term, and then employing the fundamental theorem of calculus part 2. So the antiderivative of 1 is t, and the antiderivative of t is t squared over 2 plus t to the 3rd over 3 plus dot dot dot. And we do that forever, and we're going to take it from 0 to x. Now when I employ the fundamental, I have x minus x squared over 2 plus x to the power of 3 over 3 minus dot 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 plus. Well, what is this going to be? -1 to the n, x to the n plus 1 over n plus 1 plus dot dot dot. And oops, this is an x, not a t anymore because we plugged it in. So I plugged in all the x's, and this is what I get. Now when I plug the 0 into all the terms, all of them become 0, so it contributes nothing to this power series. So the natural log of 1 plus x equals x minus x squared over 2 plus x to the 3rd over 3 minus x to the 4th over 4 plus dot dot dot. Now this is really interesting in that when we took the derivative we could not gain points of convergence, but when you take the antiderivative, when you find the integral, you can actually gain points of convergence. And it turns out the interval of convergence here will not be the same. It will not be from -1 to 1 excluding the 2, but it's going to turn out that the -1 gets included in the interval of convergence. And I'm saying that, and that's not correct. The 1 gets included in the interval of convergence. That, because at 1, it turns out is going to be the alternating harmonic. Sorry, that's the correct interval of convergence. Not that. You see, if I were to plug in -1, then all the terms become negative, and it's just the harmonic, and that would diverge. But at +1, it's the alternating harmonic. Now the last one for manipulating a known. So we want a power series for f of x equals the inverse tangent of x. Let's think of what we might know. It'd be fun to try this. We know a power series for 1 over 1 plus x squared. Do you see where I'm going with this? We did this earlier on when we looked at the geometric, which looked like this with an interval of convergence between -1 and 1. And now the relationship, or the note, now or note, doesn't matter, that the inverse tangent of x is the integral of 1 over 1 plus t squared dt from 0 to x. And let's do this now. The integral from 0 to x of 1 minus t squared plus t to the power 4 minus t to the power of 6 plus dot 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 dt. And I'll integrate term by term by term. So I have t minus t to the power of 3 over 3 plus t to the power of 5 over 5 minus t to the power of 7 over 7 plus dot dot dot. And I will take that from 0 to x. The x will contribute, and the 0 will not contribute to the power series. Wow, I don't know if you know this. This looks a lot like another one we did. Looks a lot like sine. The only difference is for the arctangent, they're not factorials in the denominator. Okay, so there it is. And we will also find that at the endpoints, again, we can gain endpoints when we integrate, and it turns out that both endpoints get included in the interval of convergence.